Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
A very good day to everyone, and thank you so much for joining today's session. Welcome to the AI for Good Machine Learning 5G Challenge organization. My name is Thomas Pascal from the International Telecommunications Union, ITU. The ITU AI and Machine Learning 5G Challenge aims to create a community to solve network-related problems using AI and machine learning. Today, we are very excited to host yet another interesting webinar for the 2022 ITU AI Machine Learning 5G Challenge problem statements. This webinar is titled Multimodal Sensing Aided Communications and the Role of Machine Learning. As always, we are counting on you to help create an engaging discussion. If you have questions, please type them in the video wall, and of course, we will take them during the Q&A session right after the talk. At this point, I would like to introduce today's speaker. The session is going to be given by Ahmed Al-Khatib, who is an assistant professor in the School of Electrical, Computer, and Energy Engineering at the Arizona State University. Ahmed received his Bachelor of Science and Master's degree in Electrical Engineering from Cairo University, the PhD degree in Electrical Engineering from the University of Texas at Austin. He was a wireless communications researcher at Connectivity Lab, Facebook in California. His research interests are in the broad areas of wireless communications, communication theory, signal processing, machine learning, and applied mathematics. He is also a recipient of several awards. In today's talk, this is the challenge webinar, which is going to explore the use of sensory data, such as radar, LiDAR, camera position, etc., as well as machine learning to address challenges that makes it hard for millimeter wave in 5G and above, 100 gigahertz in 6G and beyond systems to support mobility, maintain high reliability and low latency. The talk will also present DeepSense 6G. This is the world's first large-scale, real-world multimodal sensing and communication dataset. It enables the research in a wide range of communications, sensing, and position applications. And of course, at the end of the presentation, he will introduce the problem statement. This is the challenge that is going to start very soon for multimodal sensing aided beam prediction using real-world measurements from the DeepSense 6G dataset. So welcome, Ahmed, and good morning.
Yeah, thanks, Thomas, for the introduction and for the invitation. Would you like me to share start video? Okay, perfect.
Yes. Yeah.
Right. So thanks again, and thanks everyone for attending. And with that, I guess you can start maybe sharing the screen. Okay, perfect. You see the screen?
Yes, perfect.
All right. So in today's talk, as Thomas introduced, we would like to present some of the kind of recent research on leveraging different sensing modalities to help communication systems. So we start with the motivation, and then we'll go to DeepSense 6G, which is a dataset that enables the research in this direction. And then the last part of the talk, I will introduce a multimodal sensing aided beam prediction challenge, which is a machine learning competition that we are organizing this year as part of the ITU AI ML and 5G challenges and in collaboration with Qualcomm. All right, so let's start with the motivation for multimodal sensing. So first, currently in wireless communication systems, there are certain key trends. Two of these key trends are the use of large antenna arrays. So we go from different forms of using large antenna arrays as massive MIMO at low frequency or millimeter wave terahertz MIMO, cell-free MIMO, and intelligent services. All are different ways in leveraging larger and larger antenna arrays. There is also another key trend in migrating to higher frequency bands, so going from sub-6 gigahertz to millimeter wave in 5G and potentially sub-terahertz in 6G and beyond. So these two key trends in communication systems are mainly driven by and motivated by the need to higher data rates. So we need higher data rates to deploy larger and larger antenna arrays to get higher multiplexing gain, higher array gain, higher signal power, and then higher data rate. Or we go to higher frequency bands to access larger bandwidths and then get higher data rate. So the demand for higher data rate has been the main, let's say, driver for these two key trends in communication systems. The challenge, however, is that these two key trends bring a certain set of challenges. So for example, if we look at the use of large antenna arrays, now if both the base station and potentially also the mobile user deploy large antenna arrays and narrow beams, then setting up the link will be associated with high training and feedback overhead, which makes it hard for these large antenna array systems to support highly mobile applications. And also this affects battery life of especially the UEs that will need to continuously search and estimate the channel and search for the beamforming directions. The other key trend in communication systems, which is going to higher frequency bands, it also comes with its own set of challenges. For example, as we go to higher frequencies, the signal propagation becomes very sensitive to blockages because of the high penetration loss and the high diffuse scattering. So the communication links become mainly dependent on line of sight links. And any blockages could suddenly disrupt the communication session. And this affects the reliability as well as the latency of the communication system. So basically, if the link, let's say, is disconnected, the user will need to search for another base station and hand off to this other base station and so on in a reactive way, which incurs high latency. All right, so now if we look broadly at these two sets of challenges, we can say that in general, acquiring the channel knowledge could be a key. Acquiring the channel knowledge with low overhead could be a key to overcome these challenges. So, for example, if we have the channel knowledge, let's say if we can obtain the channel knowledge for free in terms of wireless communication resources or with very limited overhead, then the base station and mobile user will be able to figure out the best beamforming directions, and this will reduce also the power consumption. Enable highly mobile applications. And also if we have a way to know the channel, not just at the current instance, but also in the few, let's say, hundreds of milliseconds in the future, then this would potentially enable the network to make proactive decisions. So for example, it can proactively predict that a blockage will happen. And then based on that, it can proactively make decisions, let's say, to hand off this user to another base station, enhancing the reliability and reducing the latency of this switching. So if we have a way to acquire the channel knowledge for with very limited overhead or with, let's say, free in terms of wireless communication resources, then that could be a key enabler for these applications and could be a key solution to overcome these challenges. So here it's interesting to ask why machine learning and sensing multimodal sensing could be interesting. So let's first look at machine learning. So the general intuition why machine learning could be interesting in acquiring the channel knowledge, and especially in large MIMO and millimeter wave and higher frequency bands, goes back to the general intuition that the channels are generally defined by the various, the general understanding that the channels are generally defined by the various elements of the environment. So for example, we can generally write the channel vector as a function of the different elements of the environment, including the environment geometry, transmitter receiver locations, electromagnetic characteristics of the different materials, and so on. But then this function is hard to characterize analytically and changes from location to location. And this is one main reason why machine learning could be interesting. So we can potentially leverage a machine learning or use a machine learning model to learn and approximate this unknown and hard to characterize mapping function that maps the different elements of the environment, geometry, materials, locations, and so on, to the channels and beamforming vectors channel covariances, and so on. So the key point here is that, or the key trick is that if we have a way to extract and obtain some features that represent these inputs, and such that these features could be acquired with low training overhead, then using this machine learning model, we can potentially be able to map these features to the large dimensional channel and beamforming vectors that would otherwise require large training overhead. So this is basically kind of the key intuition why machine learning could be interesting in this particular context of leveraging different information about the environment to help in obtaining and large dimensional channel vectors with low training overhead. Now, the next question is, what are these features that could represent the, how can basically we capture these inputs, the environment, geometry, materials, locations, and so on. Now, interestingly, as we go to higher frequency bands and larger antenna arrays, as we discussed, so these basically trends bring new challenges, but interestingly, in the same time, they also make the communication channels more dependent on the locations of the users and scatters and so on, as well as the geometry and mobility patterns and all these kind of geometric characteristics of the communication environment. So in other words, if we know the user position, the geometry of the environment, the scatters, mobility patterns of the scatters, and the shapes of the scatters, and so on, all this information could be very useful in capturing the features that could be useful in acquiring the channel knowledge or mapping to the channel knowledge. And here comes basically the motivation for sensing-aided communication, where or in general, multimodal sensing-aided communication, where we envision the infrastructure and nodes, as well as the mobile nodes and user devices, all will have different sorts of sensors, all the way from GPS to LiDAR, radar, camera, and also wireless sensors, such as antennas, sensing the spectrum, and so on. And then all these different sensors acquire a lot of information about the environment, including the positions of the different users and scatters in the environment, the orientation, shape, mobility patterns, weather condition, electromagnetic characteristics of the materials, and so on. And then all this information could potentially be, could basically provide a lot of awareness about what's happening in the environment and the environment geometry, characteristics, and so on. And all this awareness could be leveraged by the network to make important decisions on, let's say, where to point the line of sight beam instead of searching over, blindly everywhere. So maybe if the base station knows that the user is in certain location and knows that, for example, that there are no scatters or no blockages that are blocking this link, so it can this can help at least reduce the search space. So instead of searching everywhere, so it at least will search in certain directions, or in blockage prediction. So, for example, instead of the network waits till the link is disconnected by a blockage and then reactively handoffs this user to another base station, it can, if the network has some awareness about where are the blockages and their mobility patterns and where is the user and so on, it can potentially know in advance that this link is going to be blocked, let's say, after 200 milliseconds. And then it can use this knowledge to proactively make decisions on handoff or user scheduling or beam switching, and all these kind of proactive decisions could be very useful in enhancing the data rate, reliability, latency, mobility, resource utilization, generate the performance of these wireless communication networks. All right, so now the next question is, what are these sensors could be generally divided into two main categories. One is, we can look at the wireless communication receivers as sensors. So basically the antennas and the electromagnetic signals and that waves that comes to these antennas and sensed by these antennas, they also include a lot of information about what's happening in the environment and the geometry, as well as the spectrum. So this information could be, or the antennas could be also seen as one type of sensors. The other class of sensors, we can look at it as this class of non-communication multimodal sensors, such as position, camera, LiDAR, radar, and all these sensors, if equipped at base station or the mobile user, they also provide a lot of important information about the environment, geometry, locations, etc. And then all this information could be, again, very useful in forming this awareness about the communication environment. So in this talk, I will focus on the second class of sensors, and then so let's start with basically initial results that were developed over the last few years. And we're trying to kind of just draw some insights into the gains that we can get by leveraging these different types of sensors. So the first intuitive, I think, sensing modality that was investigated is the position. So if we know just the position of the mobile user, then this potentially could be very useful in predicting, let's say, the beam forming direction, especially in high frequency line of sight communication scenarios where the length could be, again, line of sight, and the position could be very important in defining the direction of this beam forming vectors. So the advantage here is that positions could be acquired with low training overhead. Maybe simple machine learning model could be used to learn this mapping between the positions and the chance. So potentially we maybe don't need advanced, let's say, neural network architecture. So maybe lookup table could be sufficient. So that's kind of the general intuition for the advantage. Now, the problem is that location itself may not be sufficient, because the same location, basically, let's say, if we look at beam forming, a beam prediction problem, so the same location could map to different beams, depending on whether it's line of sight or non-line of sight, and what kind of non-line of sight scenario we are considering. So position data, just the position data may not be sufficient for accurate beam prediction in general for line of sight and non-line of sight scenarios. They could help, they could maybe reduce the training overhead, but potentially we can do more if we have more sensing modalities. So the second, or another sensing modality that got a lot of interest over the last few years is radar. So if we imagine if the base station has a radar device that can also sense the communication environment around this base station. So this information that we get from the speck scattering and the reflection from the different scatters in the environment could potentially help in beam alignment, and could also maybe help in beam tracking, that if we know, let's say, using Kalman filtering and other approaches. Now the question here is that, well, this radar-based solutions that were mainly developed and studied based on synthetic data, so just simulation and synthetic, will this actually be, can we take this really to reality, and will this be, will these gains could be realized in practice with, with noisy radar measurements and with practical numbers of antennas, as well as realistic scenarios, so let's say with multiple vehicles and so on. Another modality that also got a lot of interest in the last few years is vision. So vision camera, let's say, data or visual data that would be, let's say, acquired by different sensing device, such as cameras at the, or RGB or depth cameras at the infrastructure, or AR, VR, or vehicles and so on. So these cameras are already there in many of the devices, and they can provide also useful information about and rich information about the communication environment. Now, this becomes particularly interesting as we go to higher frequency bands, because the links at these higher frequency bands are mainly line of sight. So the base station and mobile users, they actually they are visually in a visual line of sight as condition in many cases. And so if the base station has some visual information about the environment, and it sees that where is the user actually using the cameras, this information could potentially help in reducing the beam training overhead, for example. So instead of searching everywhere, the base station can search only where the direction, at the directions where the user is. And it could also be useful, let's say, in blockage prediction. Again, if the base station sees the user and sees also maybe a bus coming to block the link, so it can proactively make decisions on handoff and user switch, beam switching, and so on. So in order to enable this kind of this set of research directions, we proposed first this ViWi dataset, a vision wireless, called the vision wireless dataset, a few years ago, and that was just a synthetic dataset, so based on Wireless Insight, which is an accurate 3D ray tracing, and Blender, which is a accurate game engine. And the idea here is that we wanted to have a data set with coexisting communication, wireless, as well as visual, in this case, modalities. So we want to have basically these two sets of data modalities coexisting in the same time. For example, when the vehicle is at this particular location, this is the wireless communication channel, and this is the visual RGB camera, let's say, scene, and so on. So in order to do that, we build this coexisting data of VIY, where we basically build a 3D model, import it to the ray tracing, generate the wireless data, and also in the same time import it to a game engine to generate the visual and RGB and depth information and so on, and then put this together in a synchronized way. And this is a way to have this sort of multimodal sensing and communication data. Again, that was just a synthetic data set, but kind of was an initial enabler to study some of these research directions. And then we studied this in let's say, can we use this visual data to help in beam prediction, or can we use the visual data to help in blockage prediction? And we saw some interesting results. But then the question was always that, okay, this is interesting, but can we really realize these gains in practice? Now, in reality, this different sensory data will have different source of noise. And also, so the quality may not be sufficient. There is a question. How about latency? If we use these different sensing modalities or these different sensors to acquire data, these different sensors incur different source also of latency, from the acquisition latency to the pre-processing latency to the machine learning inference latency and so on. So will this latency be a bottleneck to harvest these gains that we can potentially get via these sensory data? Also, how about realistic scenarios where we have multiple objects? So here, most of the research I have kind of discussed so far studied maybe just one object in the sensing scene. Now, if we have multiple objects, let's say, how will the camera be able to differentiate between the users that it wants to communicate with and the other distractors in the scene? How much data also is needed for training and for learning? How about transfer learning? And all these kind of interesting questions that would come, as we start thinking how to take these different machine learning applications using multimodal sensing aided communication to real deployment. So we will need to answer many of these interesting questions. And in order to enable the research in these directions and try to draw some insights about the answers to these questions, so we worked on building this large-scale real-world data set a few years ago, and we released it earlier this year, which we call DeepSense. And the idea of DeepSense essentially is very similar to the VIY, but on real data. So we have multimodal sensing and communication data that are synchronized and coexisting in the same in the same time for the same scenario. So, for example, in some scenarios, we have base station node, mobile user node, unit, and then every one of these units has multiple sensors, from position to camera to LiDAR to radar and so on, as well as millimeter wave, as well as different communication devices such as millimeter wave transmitter receivers. And then we collect the data in a synchronized way. So, for example, when we have this millimeter wave beam training results, we had this camera RGB data, and we had this radar IQ image, and we had this slider sweep, and so on. So now with this coexisting sensing, multimodal sensing and communication data, we can now start, studying all these interesting questions on can we use all these different modalities to help in these different communication systems, communication applications, as well as also, can we also leverage this different communication plus sensing modalities to help maybe sensing as well and positioning applications. We have also collected this data for multiple, for different scenarios, for V2I, V2V, drones, RIS kind of scenarios. And we have also, currently we have mainly millimeter wave. We are also adding sub-6 GHz MIMO as well. So, so this resulted in again the dataset that we call DeepSense 6G, which is publicly available now, and it has more than 1 million multimodal data points divided over more than 30 scenarios. So the 30 scenarios include, again, vehicles, human, drones, robots, kind of in a more kind of controlled indoor environments. And the multimodal sensing data include beam training power, radar IQ, raw data, camera RGB images, and sometimes depth images, 2D and 3D LiDAR sweeps, and accurate positions for both indoor and outdoor. So, and the structure of DeepSense is we structured DeepSense essentially in two ways. One way is scenarios. So we have scenario is like large data collection session. And it's defined in a standard way by the table, defining how many units, what are the sensors at every unit or terminal, and what are the sensing modalities that we are collecting, and how many data points. So now we have basically these so far 30 scenarios, and we are adding more and more scenarios to cover more and more important use cases. So this is kind of a scalable, standard and scalable way to add new scenarios. And we are also, as part of this, we are also excited about collaborating with other groups. And this is actually part of the real goal of the main goal of this dataset is to be a community dataset where we don't think this dataset can really scale to cover, you know, the more and more use cases of interest without collaboration and contributions also by other groups. So we have currently a few active collaborations with others to add, also other groups to add more and more interesting scenarios, I would say, for joint sensing and communication and sub-6 GHz massive MIMO. So this is one sample scenario where we have position data, as well as RGB beam training power, LiDAR, this is 2D LiDAR, and then radar data for range angle and range velocity. We also provide the IQ data for the radar, so we can kind of, you know, there is room for innovation, different pre-processing solutions. So with this data set, we think could potentially enable a wide range of machine learning applications, both in communication, such as beam prediction, tracking, blockage prediction, handoff, proactive resource management, and so on, as well as in positioning and sensing, such as object detection, classification, ranging. And the main, objective was all kind of to have a way to really study these interesting machine learning questions, and synthetic to real data, transfer learning, few-shot learning, data fusion, and all these interesting machine learning questions that now we have real data set that's collected from multiple locations and with enough variance and diversity that we can potentially start using to kind of look at these interesting questions and start driving some insights about these questions. All right, so the other way we are providing this data is in a more kind of standardized, task-specific data sets, development data sets. And this is mainly kind of, the objective here is mainly to enable benchmarking, to facilitate benchmarking and reproducibility of the algorithms and solutions. So for example, so far we have 2-3 tasks between current beam prediction, future beam prediction, future blockage prediction. And for every task, we have different modalities. And again, so for every modality and every task, we have a specific data set, so specific training, validation, test set, where now basically anyone interested in studying this, let's say, how can we use, let's say, visual data for current beam prediction, can now download this data set, develop interesting machine learning model, get better results, and submit it to this online ranking table or leaderboard to kind of have the benchmark and then maybe share the code. So this is a way to now we all can basically compare algorithms based on the same ground and enable benchmarking and reproducibility of the results. All right, so in the next 5-10 minutes, I will go over a few applications that are enabled by some example applications that are enabled by this DeepSense dataset, and then we'll go to the definition of the competition. All right, so one important example, of course, is sensing-aided beam prediction. So if we have these different data modalities now, we can revisit all these interesting questions about, can we really use a position, LiDAR, radar, camera data, all these kind of data modalities to achieve good beam prediction accuracy and reduce the beam training overhead. So instead of searching again everywhere, can we reduce this beam training overhead by leveraging these modalities? And can we really see the performance on real data and real scenarios and realistic coherent scenarios? And the point here is that if we can develop solutions that perform well in these realistic scenarios, then this could potentially mean that they have real practical significance. So we studied this. We just draw some kind of very initial, try to kind of get some initial results, I would say, into the some of these modalities for beam prediction. But I believe there is very, very big room for improvements and innovation. So this is really just scratching the surface. So one problem we looked at is how useful GPS positions actually are. So if we, again, using synthetic data, intuitively, we think that if we know the position, we can directly just predict the beam, and maybe a simple lookup table could be enough. Now, if we look at real data, real GPS, let's say, data, where it could potentially have some noise, also the beam training, so the beam forming vectors themselves, the beam patterns themselves, they may also have some noise, they may have some overlapping, and so on. So all these noisy data for both the inputs and outputs, the position and beam, how would they affect the beam prediction accuracy for something very simple such as position-aided beam prediction? It's kind of, I mean, intuitively simple, let's say, problem. So to study this or to draw some insights, we adopted 9 scenarios from DeepSense and different codebook sizes. So here's the good thing is that we have a beam training of 64 beams codebook. So we can now sample it to have smaller codebooks. So we can have 32 or 16 and so on. We also looked at different machine learning models from simple lookup tables to more advanced neural networks. And then the question was, one of the questions was, can we get the same performance that we expect from synthetic data, like 90% or something? So these are some of the results we got. So here we have, we compare top K beam prediction accuracy for different K and for different machine learning solutions. So in summary here, what we see is that if we use the position to just predict the best beam directly, then the accuracy is not more than 30, 40, in some cases, maximum 50-something%. So it's not really 90% as we would expect, let's say, from synthetic data or what we have seen before in synthetic data. And the reason here goes back to the noisy inputs, positions, as well as the noisy labels. Those labels themselves, also the beams themselves could be also noisy. And another important question here is that now if we look at, let's say, top 3 or 5, then this can go all the way to 90%, which is, of course, still promising because now we can, this says that we can use the position to at least narrow down the search space from 64 to 5 beams, which is still a huge reduction in the beam training overhead. Now, another important question was, here is the top K beam prediction accuracy a good metric? I mean, is this the right metrics that we should use? And here it's important because the top K just says look at whether or not the top K predicted beams by the machine learning model include the ground truth beam. Now, in reality, they are not including, or maybe even the top one may not be the ground truth beam, but it could be very close. So in that case, the accuracy could be very low, but then because it's very close, we can still actually get good beam good SNR or good receive power. So that's why we looked also at the power loss. And what we see here is that even when the beam prediction accuracy is low, the power loss is 10 within 3 dB, which is not low. So this again, I mean, just highlights the importance for using the right performance metric. And this is something that we are also considering in the machine learning competitions that we are organizing. Another modality we looked at is radar. So, and the question here is that, again, I mean, can we use this radar data to reduce that overhead in beam training in millimeter wave systems? So now the good thing in radar is that as a community, we know a lot of signal processing that we can do for this raw data. So instead of just feeding the raw data directly to the neural network, we can potentially extract useful features by some, processing, signal processing for the radar data. We can, for example, extract the range, angle, range, velocity, and so on data features, and then we can maybe rely on these features because they have already a lot of information about the user location and mobility pattern that we can use in the machine in the beam prediction. So the data we used here is a result of is obtained by an FMCW radar, 4 gigahertz bandwidth, 3 transmit, 4 receive antenna, so relatively low resolution radar. And the question we use this to predict the beam training, the optimal beam for a 60 gigahertz millimeter wave front end with 16 transmit receive antennas. So what we see is, so I have, of course, more information in this paper, but just in summary. So one thing is that in general, I mean, even with this low resolution radar, we can still potentially achieve, again, more kind of close to 90% beam prediction accuracy with 5 beams. So kind of, again, the radar could reduce that training overhead to 5 beams with more than 90% accuracy, which seems promising. Now, also, we see some good gain from machine learning solution, more advanced machine learning neural network-based solution compared to classical lookup table or simple machine learning, low or shallow machine learning solutions for this problem. We also looked at the inference and here and the complexity of the different solutions. And one important thing here is that the inference latency, or in general the latency that we see here in the radar, similarly also for visual data, let's say, is in tens of milliseconds. So of course this is a different time scale compared to communication systems that work in a few milliseconds, maybe want to finish this beam training in a few milliseconds. So now if we rely on radar or LiDAR or camera, so this may need tens of milliseconds to predict the beam. And this opens, an important question about whether this latency is a bottleneck or can just make all these like sensing aided communication ideas maybe not useful. And what I think here is that this significant latency, I would say, from communication perspective, may make the current beam prediction or current, let's say, may make it hard to use the sensing data to use it to do a real-time prediction. But you can potentially use the sensing data to make some prediction for the, let's say, near future or near real time, or the next, let's say, 10 to 100 millisecond prediction. So, for example, we can use this radar data. Let's say the radar data collected for a sequence of 3, 4, 5 samples to predict the beam for the next 4 or 5 coherence times or instances that are maybe that will maybe spanning 400, 500 milliseconds. So in that case, prediction. So in that case, this latency may not be a problem. So we can again use maybe acquire the radar data in a few hundreds of milliseconds, and then use this radar data to predict the beams for the next 400, 500 milliseconds. Another important question in the sensing-aided communication applications is, what about if we have multiple objects? Okay, how about having multiple objects in the visual scene, for example, or in the sensing scene in general? So, for example, if we rely on this vision-aided beam prediction, if we rely on the visual data to predict the beam to the mobile user. Now, if we have just one vehicle, let's say, or one mobile user in the visual scene, it is simple object detection, and then learning, the mapping between just the bounding box, let's say, dimensions to or locations to the beam, which is kind of a simple mapping intuitively. But then, how about the case when we have multiple maybe vehicles or multiple objects in this visual scene? How will the camera be able to do, or the base station be able to differentiate between the transmitters or the users that it wants to serve and the other distractors? So in order to do that, so we need to do what we call transmitter identification or user identification. So here, if we have more than one object in the sensing scene, so we need another attribute for this for the user, so that we can now fuse this sensing modality plus this other attribute together to be able to identify the user in the visual scene. So, for example, in this particular work, we use the RGB images and location data of the user. So fusing them together to be able to identify where is the user and track it and be able to do beam prediction to serve this user. Now, why not just position? I mean, visual, we believe that with visual data, we can do, first, we can actually improve the positioning accuracy. And second, this can scale to non-line of sight applications as well, where the user may not, the location itself may not be sufficient. So this is a live demo that we have done before, where here, as we see, so we use the visual data and position data to predict the beam without using any communication resources. So here, essentially, the system is doing this beam prediction and beam alignment without using any wireless communication resources. So it's kind of, almost for free in terms of wireless communication resources. It's just using, again, other modalities that are obtained from the camera and position data. And as we seen, so the base station is able to identify the transmitter, even if there are other distractors in the visual scene. Okay, another important application that I will maybe skip some of it is blockage prediction. So this is another important application, in our opinion, for sensing data. Now, blockages are key challenges for communication systems at higher frequency, millimeter wave and sub-terahertz. As we go also to kind of even 6G and sub-terahertz, this becomes more and more challenging problem, where almost any blockage could, or any object could block the link, the line of sight link, and could abrupt the session, will have a lot of impact on the reliability and latency of the communication network. So if we have a way with machine learning and sensing to, again, predict the blockage before it happens, so predict future blockages, then this can, again, potentially gives the network opportunity to make proactive decisions. So to look at, again, to kind of investigate this problem, we collected data for this particular blockage to enable this, or multiple scenarios to enable this, studying this blockage, proactive blockage prediction problem, using both wireless data, just relying on let's say, the signatures that would be there in the beam training. So if there is a fixed transmitter receiver, and they do beam training as part of their typical communication process. Now, if we look at the beam training, the power of the beam, of the different beams versus time, then they could interestingly capture these blockages that are coming and approaching the line of sight link before actually they block the link. So there is a bus, let's say, that's coming closer to this line of sight link between the transmitter, which you see in the scene, this red circle, and the receiver where the camera is taking this photo from. So this line of sight link is continuously doing beam training. And then as this bus gets closer and approaches this link, then it acts basically as a scatter, and it will have some signature in this beam training power map. And now, interestingly, with machine learning and neural network, it can effectively learn these signatures. And using these signatures, it can predict whether a blockage will happen or not, and when it could also happen. So we have some kind of interesting results on this wireless signature-based proactive blockage prediction in this paper. And in fact, what we found is that, interestingly, these signatures could be used not just to predict whether a blockage will happen or not, but also to differentiate between the different types of blockages. So we can actually, using this signature, we can know whether this incoming blockage is a bus or a small, let's say, car, and things like that. So that's kind of interesting. And then we have also radar data to study the same problem with LiDAR or radar. So this is, for example, radar data that we can also use to study kind of similar problems for blockage prediction, future blockage prediction. All right, so in the last 5 minutes now, I would like to introduce this hopefully interesting machine learning challenge we call multimodal beam prediction. And the objective here is really to go towards generalization and to investigate how generalizable can we develop basically solutions that generalize as well to unseen scenarios. So this is a competition that we're organizing first as part of the AI for Code, ITU, AI ML 5G challenge. and in collaboration with Qualcomm. So the idea here is to leverage this, again, to focus on this multimodal beam prediction task. And we collected, for this challenge, we collected four scenarios. So data at 4 scenarios. What we think are realistic scenarios. So this is, let's say, a street. Here we have, again, the visual data, the position data, the beam training power, 3D LiDAR, and radar. All collected, again, from on the same setup, from both the base station node, where you see this visual data from, and the mobile vehicle that you see here traveling around the base station. So we have 3 of these, we have 4 of these scenarios that, again, collected in different parts of the city. And then the question is that we're asking is, can we use this multimodal sensing data collected from the RGB camera, the LiDAR, radar, and position to help in predicting the beam? So if we can do that in such realistic, challenging data sets, then, and if this solution can generalize well also to unseen scenarios, then hopefully this means that we have a very useful and important machine learning solution that could potentially, address and this very important beam training overhead challenge that is one of the most critical challenges in 5G and 6G as well. So in particular, the problem statement is as follows. Now we have, again, an infrastructure node that's collecting data for mobile users in these kind of realistic scenarios that you have seen. And the problem is as follows. We have data points. Every data point is collected over 5 samples in time. So the spacing between them is 200 milliseconds. So now we have basically 5 RGB images collected for, in a sequence of 200 milliseconds spacing, and 5 radar samples, 5 LiDAR, and the 2 positions that correspond to the first 2 samples. So this together is 1 data point. So now if you have this data point, again, the sequence of samples, can we design a machine learning model that predicts the beam of the 5 samples? So essentially the base station is sitting there. It captures camera photos, images, or RGB images. It captures radar, LiDAR, and it gets the position of the vehicle, the GPS position from the vehicle for the first 2 instances. If the base station node has this information, can it use this information to predict the beam of the 5th instance, which is the current instance, okay, with high accuracy? So this is basically the kind of the problem statement. On the website, of course, you will see kind of more details and more formal also kind of description of the problem. Now, why, just kind of drawing kind of quick insights here on why we have only the position for the first 2 points. I mean, what we think is that this could be an interesting challenge, because in reality, this position, and if there are GPS positions, they will be fed back from the vehicle, so we have additional latency. Maybe also the GPS and so the LiDAR, radar, and RGB, they could be sampled with higher frequency compared to the GPS. So GPS normally 10 samples per second, while the other modalities could potentially be higher. So for example, cameras, you can have maybe 30 frames per second, or radar and so on. Also, this may form realistic scenarios where in some cases, some of the data modalities may be missing. So may not have all the modalities all the time. So we thought this could be an interesting challenge. Also, this kind of motivates more, really exploring the value of adding RGB or radar or LiDAR to position. So, compared to position, now if we have these additional modalities, how much more data rate how much more accuracy we can get. So the development data set in particular, so we have again 4 of these scenarios. We have 3 of them, mixed data of 3 of these scenarios as the development data set that is provided to the participants in the beginning of the competition. And they include around 10,000 multimodal data points. Every one of these data points, as I described, has these 5 samples of RGB radar LiDAR and 2 samples of position. In addition to the ground truth beam training, actually the full beam training, the ground truth beam training sweep, 64 beams at the 5th sample. Now, given this data set, the objective is to, again, design a machine learning model that can effectively predict the beam, the optimal beam, as well as generalize, as well as it can generalize well for unseen data. So in order to kind of test this, so the test set has 2 parts. 50% of the test set is collected from the same 3 scenarios that have been there in the development dataset, of course, not overlapping with the offered development dataset, but from the same 3 scenarios. And then 50% of the data is provided from a new scenario that's unseen. So now if this machine learning model can really learn and not memorize, then it can potentially generalize well to also predict the beams for this new scenario. And then the score that we used here is, or that we're using here is the score that we call distance-based beam prediction accuracy. And the objective here, again, is, as I kind of mentioned earlier, is we think that just looking at top K may not be sufficient, because even if we are close, the top K could be low, while we are actually achieving good power. So we wanted to have a score that has good correlation with the end objective of this problem, which is a communication objective. So we want a score that has meaningful communication objective, communication measure as well. So what we do essentially here is that we measure the distance between the predicted beam and the ground truth, and we consider only the top, the distance, maximum distance of 5 beams. So basically, if we are really 5 beams away from the optimal beams, and this means that we're kind of completely off. And then we average this over basically the data set, and we look at the best 1, 2, 3. So we calculate this metric for the best 1, best 2, best 3, and then we take the average. So that would be the score. So it's kind of between 0 and 100%. We also provide a baseline solution based only on position. So if you take this data point and look only at the 2 positions, then can we use only the 2 positions to predict the 5th beam? We provide a baseline solution based on this. So this could be a good baseline, because hopefully when using the radar LiDAR camera, we can get more than just using position. We also provide this in a starter code that that basically loads the data, constructs the training validation sets, run the baseline, and compute the baseline score. So now essentially you can use this starter code as a template for your machine learning solution. All right, so last slide. So with this competition, so we hope that it will be interesting for many people in the community. And the timeline is that we'll start in next week, offering the data and the registration. The submission of the results will be around October, and then the final ranking is towards the end of October. And then we have the final, the grand challenge in November, December. So this is, again, it's kind of sponsored by ITU and Qualcomm, and we have prizes of more than $7,000 for the first 3 winners, and in addition to $5,000 for the grand challenge. This is on the level on the scale of the full competitions. All right, so with that, I conclude. Going to higher frequency bands and using large MIMO systems are key trends in communication systems. However, they bring new challenges in mobility, reliability, latency, and power consumption. And we think that leveraging multimodal sensing in addition to machine learning could be a very interesting solution to address these challenges, leveraging the awareness about the environment to help in figuring out the beamforming direction, supporting mobility, proactively predicting blockages, which enhances the reliability, latency, and so on. And in my opinion, this is a direction with a lot of room for future research, very open for a lot of open problems in designing optimized machine learning models, looking at all these interesting machine learning questions in transfer learning, generalizability, scalability, and all that, limited data learning and data fusion. as well as looking at new applications in communication, sensing, and positioning by fusing this real data. All right, so that conclude. Thank you very much, and looking forward to your questions.
Thank you so much, Ahmed, for this rich presentation with a real-world data set. I think it's quite nice to see how rich these sensors can provide information for future communications. So it's time for the Q&A. I would invite my colleague Vishnu to moderate the Q&A, to have a chat with you on what you have discussed and what are the future directions. So over to you, Vishnu.
Thank you, Thomas, and thank you, Ahmed. Excellent talk. First question is a simple one, I guess. The visual data that you use for beam prediction, is that publicly available? As Mariam is asking. I think you answered about the multi-modal set. I guess this question came a little while behind. But let me ask you about this one, visual data that you use for beam prediction.
All the data is publicly available. I think we have now most of the 30 scenarios data. I mean, we have, I think, 27 or something out of the 30 scenarios published already and publicly available. So we have, as I said, around 30 scenarios, 1 million data points. So yeah, I mean, they're all publicly available now, and you can access them at any time.
Thank you so much. I think this is a very excellent problem statement. You know, in fact, the last couple of years, we had good problem statements on channel prediction, beam prediction, individually speaking. I mean, individually, we had these problem statements. We also had the environment-based learning solutions-based, I mean, our colleagues in Tuxel had this weather data, which we used to predict. And also there were radar data based problem statements. But I think your problem statement and data kind of brings all this together in a multi-modal form, as you say. So it's quite interesting for us. Question on indoor and outdoor. So I want to ask you about the applicability for indoor and outdoor solutions. I see that you know, you can see that all the data collection you have done outside, you see that. But is this technique applicable indoor, outdoor, and for 3D because even your y-axis inferences that you do is it looks like 2D, but I want to ask you about 3D applicability of the solutions.
Yeah, these are great questions. So for the indoor and outdoor, actually, we have also some of the 30 scenarios that we published. Some of them are actually indoor, and some of them was just humans, kind of, you know, some of my students or myself carrying a transmitter going around in the lab or in the conference room, and some of them we have robots. So robots carrying, you know, that transmitter and going around. So we have actually indoor data also as part of this DeepSense dataset, and we plan to collect more indoor scenarios soon. So yeah, so definitely we're trying to cover both indoor and outdoor applications. For indoor, we use, of course, different positioning systems rather than GPS, but everything else is the same. So we have, again, skin camera, LiDAR, radar, as well as indoor positioning. So we have data for indoor. So that's for the first question. And I think many of these problems are equivalently interesting for indoor, and beam prediction, blockage prediction, sensing and positioning. And of course, positioning in particular is very interesting application for, you know, smart warehouses and industrial 4.0 and so on. Industry 4.0 and many interesting indoor applications. Now for the 3D data, I mean, so both the radar, I mean, LiDAR, I mean, actually we have 3D data as well. So LiDAR in particular, we started adding 3D LiDAR recently. So this competition data, at least we have interesting 3D LiDAR data. The radar data is general. I mean, it's mostly let's say ULA kind of antenna array. So it's mostly, maybe you can think of it as a 2D maybe, but and the beam training power is also in 2D so far. But yeah, I mean, I believe for at least the beam training, I mean, the 2D kind of, let's say, solutions would be somehow extendable to 3D.
Thank you so much. There is a question from potential participants, which we shouldn't miss. Namalidin is asking, is it compulsory to use all the modalities, or can we pick and choose from which data we train? Maybe any two of the data sets. Yeah.
Excellent question. Yeah, sorry, I forgot to mention this. Very, very good question. No, actually, so what we eventually decided to do in this competition is to offer this multiple modalities, and then it is up to every participant or team to choose the modalities of interest. So you can choose just to use position, and in that case, you use 2 position to predict the future beam, or to use, again, position plus vision, LiDAR plus vision plus position, you know, any or all the modalities together. So it's no constraints on using the, you know, which modalities.
Thank you so much. There is a question from Mudassar. He's asking how many models we should train for each base station one, or is it the same one model that we apply through the network?
Yeah, it is one model for the full data. So we provide just one data set actually. So so this data is constructed from 3 scenarios, but we mix them together, shuffle and mix and everything. So we have only one development data set that is, you know, the result of 3 scenarios. So we need just one model that can work on this data, as well as that can hopefully perform well on the test set.
Thank you so much. About your baseline code that you had in one of the slides, you had mentioned a starter code that is provided. That's excellent. I believe this makes a lot of difference for the participants. So from our experience, it makes a lot of difference. So in this, what kind of requirements do we need? Do we need GPUs? By the way, ITU provides GPUs. Thomas will talk about it. But do we need GPUs to run this, and what kind of requirements and dependencies are there to run this, please?
Yeah, this is a good question. So first of all, I mean, the dataset size, of course, this is a multimodal sensing data. So it's, and we hope to make something that's kind of also, I mean, to have this as a kind of in a realistic setting that would have practical significance. So one point is that the data size is relatively big. So so now if you so I think the full data is around 35 gigabyte. Now you can choose to, if you are interested in only, let's say, position plus vision. So we also divided this data, or kind of we are offering the data in also subfolders, if you wish. So position, let's say, plus vision, we are offering this alone, position plus LiDAR. So there's two kind of different combinations. So that if someone is interested only in, let's say, leveraging only position plus vision data, so they don't need to download the full data. So this is one just on the dataset size. Now, on the CPU and GPU, I mean, I think the starter code may not necessarily need a GPU just to run this simple position-based beam prediction starter code. I don't think it will need a GPU. Now, if you want to kind of course, develop like machine learning solutions that would, let's say, use visual data and so on, I think we'll need some GPU computation power.
Yes, thank you so much. I would really encourage the participants to stay back and listen to Thomas. He has an announcement about the GPUs. But let us look at the latency problem that you mentioned. I believe that's an interesting question that you mentioned. I believe in one of the slides you had actually talked about the use cases. I believe use case 21. You had listed down all the interesting use cases. The important point would be to look at which one of this is really latency sensitive, and how we could tackle these latency sensitive use cases with the constraints that you mentioned. What is your opinion about this particular problem of how we can solve this real-time inference problem? You did mention actually your graphs were very interesting because you were comparing threshold-based lookup table solutions with machine learning solutions, which is actually really interesting for us. So I want to ask, do we need to look at use cases which are better off doing lookup table, better off doing threshold-based solutions versus the ones in which machine learning can really give solutions? What is your general opinion, please?
Yeah, this is of course a very important point, because latency is of course it's kind of important for communication decisions, especially real time. So now, first, I mean, this latency, it has three parts. It has, I mean, when we talk about sensing-aided communication, so there is a data capture latency, there is a pre-processing latency, and inference latency, machine learning part. Now, interestingly, the challenge is actually in this latency is mainly on the data capture and the processing. So for example, in visual data vision aided beam prediction, so what we looked at before, the capture time and processing, it could be 20-30 milliseconds. The inference time itself could be 4 or 5, I mean, could be with some, efficient quantization and pruning of the network and so on, and some efficient design of the neural network and so on, then we can maybe bring it to 3-4 milliseconds. So the inference latency, interestingly, is not the machine learning inference latency may not be the key bottleneck in the full latency overhead. The main overhead comes from the data capture and the processing. Similarly for radar as well. So that's why, I mean, it's of course important and interesting to develop low complexity machine learning solutions. Of course, I mean, and actually if also in this competition and in general, I mean, if we can solve a problem with classical solutions, that's great. If we can solve it with low complexity machine learning models and solutions, that's great. If not, then we need to go to higher complexity solutions. But back to latency. So now, given this kind of breakdown of latency, so it seems that there is something fundamental in the latency and the challenge because of the capture time and the processing. And as a result, so what I think is that eventually these sensing aided communication applications would more practically be used in a way that will not be kind of predicting again what we let's say what is the channel at the current moment or the current millisecond, or what is the beam at the current millisecond, or whether there is a blockage at the current millisecond or not, but to use this data to predict the sensing and awareness and understanding of the environment to predict something that is happening in the near future. So for example, again, let's say consider this radar aided beam prediction task. So there is a vehicle, maybe V2I, maybe vehicle moving in front of the base station. The base station is acquiring maybe a frame of radar samples. Now this frame of radar samples, it will give the base station good information about what's happening in the environment, what is the trajectory of this vehicle, what is the mobility patterns of the other moving scatters around it, and so on. And then you use this information, the sequence of radar data, to predict maybe what will be the 3, 4, 5 beams that the base station should use to serve this vehicle as it moves, let's say, in the next 200, 300, 400 milliseconds. So now if we look at something like this, like predicting future, making future prediction on the beam, so not predicting the current beam, but predicting the future beams. So that, I think, would somehow relax this, the challenge that would come with latency, because now if we are predicting something that would happen, that we will need to use in 100 or 200 milliseconds in the future, then this 20-30 millisecond latency will not be an issue. Similar,
Thank you so much.
to blockage prediction, handoff, network user scheduling, and other problems.
Thank you so much. Yes, I think the split up of latency, yes, I think that's a very good point. There is further questions from participants. Let me take those last ones. Karim is asking, do we have relative GPS or exact position of the user, and whether there are any restrictions on the number of GPUs that one can throw at the problem? Yeah, so any restrictions on the compute power? I believe that's what he's asking. Yeah.
No, I mean, we're not putting constraints on the compute power. Yep.
How about the first one, the relative or exact position of the user?
It is the exact position, so it's the exact GPS position of the So we are providing the GPS position of the vehicle as well as the GPS position of the base station. So now with the two, you can calculate the difference.
Thank you so much. And Mariam is asking, the visual data might not contain the user in case there is no line of sight. Yeah, I believe so, right? You told about in the blockage predictions case also the same thing. Can you answer that question?
So the question is what if we don't have line of sight? What if the vehicle is not
the question is that we may not be able to see the user in case there is blockage or in case there is no line of sight.
Yeah. So so this is basically a realistic scenario, right? So the user may be in line of sight for some of the cases, and then it could go to non-line of sight, and so on. And then so again, as part of like studying a realistic problem, so we want to see, what will be the best way to handle that. So maybe you can use understanding the visual scene. I mean, eventually, maybe depending on where the user goes to non-line of sight, maybe the best beam would be maybe a non-line of sight beam that will go reflect somewhere and goes to the user. Or it could be that we lose maybe the power in this 1-2 samples where the user is just passing behind a vehicle where we cannot maybe we don't have a good non-line of sight beam. So I would say this is a realistic scenario, and of course it has these kind of realistic impairments and challenges, and we are offering this as kind of an opportunity to study and open the innovation, right, for kind of room for innovation for what we can do in these realistic problems.
Very good, very good. Thank you so much. It's quite exciting. As I told you before, I think this multi-modal data set is quite new for us. I think it combines a lot of problems which we had seen earlier, and this is very interesting to combine that and take a unified look at it. I have several more questions, but maybe we should take it in one of your roundtables. We have these roundtables with participants later on, and then we will trouble you again to come and answer these questions for us. But thank you so much. We are over time. Thank you for patiently sitting and answering these questions for us, for the participants as well. And it's a very exciting problem statement as well. Over to you, Thomas.
Thank you so much, Vishnu, and a big thank you to Ahmed for coming and giving this talk. We really appreciate you hosting the challenge with real data sets. This is quite amazing, and it's really nice that you teamed up with Qualcomm to come together with us to provide this challenge in this edition. So thank you so much. At this point in time, I have a few announcements to make. As I have put some information in the chat, in the video wall. So for the participants on the neural network, you can see under the chat, there is some information that I've put across. You can see the problem statements that are available for this year. This will also include the challenge that Ahmed has also presented. We are going to make it available in a few days, and then you can start registering, accessing the data, and developing your machine learning models. We also like to announce that ITU is providing free GPUs. Of course, it's not free for all, but it's free for people who cannot manage to have a very good compute platform. So this is state-of-the-art ITU compute platform. We have GPUs that we will provide to participants of the challenge so that they can develop their models and train and optimize to make sure that they can compete fairly with other people who have access to very good compute platforms. So make sure that you join our Slack channel, check our website, check the challenge information. We have more webinars that are coming to you. The next one is tomorrow. We have another webinar for the challenge problem statement tomorrow, so please make sure that you also tune to that if you are interested. And of course, when this challenge is available, we will send out emails, announcements, so that you can register and start working on it. Thank you very much, everyone, and I would like to close at this time. So thank you to Ahmed for coming, and thanks to everyone for joining the session. Have a good day.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.